Hello everyone, welcome to my channel. Moment of inertia for grade 11. In pure translational motion, we learn about position, velocity, acceleration, mass, and Newton's law, especially Newton's second law. In pure rotational motion, the equivalent of these quantities will be angular position, angular velocity, angular acceleration, and the equivalent of mass will be moment of inertia that we presented here. And instead of F equals ma as Newton's second law, in pure rotational motion we have torque equals moment of inertia times angular acceleration. So we can see that moment of inertia is very important to solve any physical questions related to rotation. So let's start with this question. Consider a solid sphere, a solid cylinder, and a hollow cylinder rolling down a ramp. Which one will reach the bottom of the ramp first? A sphere is the first, cylinder is the second, and the last one is hollow cylinder, which reach the bottom of the ramp, one after each other. But the question is, why is that? Do you know why? To answer this question, we should know about moment of inertia. So what is the moment of inertia then? The moment of inertia tells us how difficult it is to change the angular velocity of an object around a given axis. So moment of inertia is similar to mass, but in rotational concept. It's like rotational equivalent of mass. And this quantity depends on shape of the object, its mass distribution, direction of rotational axis. So as we discussed, moment of inertia is the resistance of the object to change its angular velocity. So the resistance that we experience for a rotational object to change its motion, it's called moment of inertia. And as we said before, it's equivalent with the mass in total translational motion. Here, as you can see, we have two spheres with the same mass. But since mass distribution in these two spheres is different, we need extra effort to rotate the sphere with a larger radius. But the question is, how can we calculate moment of inertia? We need to add up the contribution of each particle in this equation. We need to add up m times r squared for all particles to find the total moment of inertia. And the unit for moment of inertia is kilogram meter squared. And for different objects, we have different formula. Depends on what geometry the object has. So, for example, a cylinder, it is 1 over 2 mr squared. And for a single mass, like a pendulum, is mr squared. So depends on the geometry of the object, we need to use the correct formula to find the moment of inertia. Now, to better understand the concept of moment of inertia, consider two wheels A and B with 10 kilogram mass each. Question is, if the wheels are made to rotate, which one will be harder to rotate? RA, radius of wheel A, is greater than RB, radius for wheel B. If we apply an equal torque to these wheels, angular acceleration in wheel B will be greater than angular acceleration in wheel A. Therefore, moment of inertia in wheel A will be greater than in wheel B. And the answer is, it is harder to rotate the wheel A than the wheel B. The key point here is that if the moment of inertia is large, it becomes more difficult to accelerate the wheel in the angular direction. And also, if the moment of inertia is small, it becomes easier to accelerate the wheel in the angular direction. So we can conclude that objects with a smaller moment of inertia accelerate faster in rotational motion. Now, let's reconsider the question 2, which asks why the sphere reaches the bottom of the ramp first. So the answer is, the object that reaches the bottom of the ramp first depends on its moment of inertia divided by mr squared. To find acceleration for each of these objects, as we can see, we need to use this general formula. This formula is dependent on the ratio of I to mr squared. For solid sphere, the moment of inertia is 2 over 5 mr squared. And if we calculate I over mr squared, we get 0.4. For solid cylinder, moment of inertia is 1 over 2 mr squared. And I over mr squared will be 0.5. And for the last object, hollow cylinder, the moment of inertia is mr squared based on the table that I showed you. And I over mr squared for this hollow cylinder will be 1. Since we mentioned that an object with smaller moment of inertia relative to mr squared has the greater acceleration, therefore we can conclude that solid sphere reaches the first, solid cylinder the next, and hollow cylinder the last object which reach the bottom of the ramp. So now we can summarize our conclusion and relate this quantity to energy. And remember the formula given above for acceleration can be obtained by energy calculation. So to summarize our calculation, we should say that the moment of inertia determines how the total energy, here gravitational potential energy, at the top of the ramp is distributed between rotational kinetic energy and translational kinetic energy. So object with a smaller moment of inertia relative to their mass and radius accelerate faster because less energy is used for rotation. Let's solve this question. Which of these pendulums will swing back and forth more frequently than the other? A or B? So to answer this question, we should pay attention to mass distribution compared to the rotational axis. As we can see, mass has been distributed farther than axis compared to figure A. Therefore, the answer is A. So B has larger rotational inertia, so it will be slower in gaining speed. Question 5. Which of these is easier, harder, or hardest to rotate about its axis of rotation? We have a pencil rotating in A around axis, which is along the length of the pencil. In B, axis of rotation is perpendicular to the pencil, and in C, axis is at one end of the pencil. So to answer this, pay attention to mass distribution. In A, mass distribution is very close to the axis of rotation. In C, mass distribution is farther from the axis of rotation. And B is between situation A and C. That's why A will be easier to rotate. B harder to rotate, and situation C is the hardest to rotate. Now let's solve this example. Two balls connected by a rod, as shown in the figure below. Ignore the rod's mass. The mass of ball, which is shown by X, is 0.7 kilograms. And the mass of ball Y is 0.5 kilograms. What is the moment of inertia of the system about axis of rotation AB? So first we need to sort the information given by the example. We have mx, my, rx, ry. To find the moment of inertia for this mechanical system rotating about axis AB, we need to use this equation. We need to add up the contribution of mass x and mass y. So mx rx squared, by substituting the quantities given above, will be 2.8 kilogram meter squared. And my/ry squared will be 32 kilograms meter squared. Therefore, the final result will be 34.8 kilogram meter squared. Now, let's compare this situation with the situation in which rotational axis passes through mass x. Rx is 0 because there is no any distance between axis A prime, B prime to mass mx, but ry is 10 meters. So again, total moment of inertia is mx rx squared plus my ry squared for the axis A prime b prime, we have mx rx squared 0, because rx is 0. And for my ry squared, we get 50 kilograms meter squared. So we can add up these two to find the total moment of inertia, which is 50 kilograms meter squared. If we compare this moment of inertia with the former one for the axis AB, we conclude that IA prime B prime is greater than I about axis AB. Now let's summarize what we mentioned so far briefly here. In simple terms, moment of inertia is the resistance of the object to spinning or rotating. Objects with a smaller moment of inertia accelerate faster in rotational motion. And we learned that moment of inertia depends on shape of the object, its mass distribution, and the direction of rotational axis. And in general, to find moment of inertia for point masses, we can add up the contribution of each particle in this formula by finding mr squared for every particle that we have in our mechanical system. And remember, unit of this quantity is kilogram meter squared in SI. Thank you for watching this video. Please follow other videos in my channel by subscribing.